The next concept is ROC curve. Now, what we have seen is if you change the threshold value, let us suppose usually what is the threshold? When do you say, like by default, where is the threshold that is kept?
0.5.
0.5. Anything above 0.5 is called as class 1. Anything below 0.5 is called as class 0. That's the default threshold value. If you want to focus on class 1, you will reduce the threshold. If you want to focus on class 0, you will increase the threshold. Okay. By changing the threshold values, your sensitivity and specificity changes. Earlier, we told that 0.2 is the threshold that you can keep to increase the accuracy of class 1. Okay. Now, what is the optimal point where you can put this threshold value? What is that optimal point? Is it 0.2 or 0.25, or shall I keep it at 0.3, or shall I keep it at 0.15? Like, I know that I have to reduce it from 0.5 to some lower number, but what is that optimal point where I can keep the threshold so that I can give some preference to class 0 and a lot of preference to class 1? It should not happen that we don't give preference to class 0 at all. For example, class 0 is a bomb. I know class 0 is no bomb. I know that you're not interested in no bomb cars. I know that you're interested in finding out the bombed cars. Imagine you're keeping the threshold at 0 itself. What happens if you keep the threshold at 0? What will happen? Tell me. The first car comes. The probability is 0.12. What will you do? You will classify that as
1.
Bomb. Second car comes. The probability is 0.001. You will classify that as
Bomb.
bomb. So 1 lakh cars have come to you. You will say all these cars are having bomb. Do you think it's a good scenario? Is there any model there, or it is simply giving everything as bomb 1 only? If you follow this approach, definitely you will find the car with the bomb. But is it optimized? Is it the right way to go about it? Do we need a model there?
Yes.
It's a brute force method, isn't it? So I agree that you have to reduce the threshold, but there has to be some preference given to this class also. Yes or no? Imagine this is bad customers. 1 is bad customer. 0 is good customer. I agree that finding a bad customer is very important for you. I agree that class 1 is very important for you. What happens if you keep threshold at class 0? What happens if you keep threshold at 0 itself? First customer applies. What will you do with his application? Whatever is his score, what will you do? Decline. If you keep on declining, you got 1 lakh applications. How many applications will you decline?
1 lakh.
All 1 lakh. Are we going to do any business if we do like that?
No.
Yes, I agree that class 1 is very important for you. Does that mean class 0 is utterly not important for you? There is some preference that should be given for class 0, isn't it? Higher weightage should be given to class 1. So how do you decide that right threshold, 0.2 or 0.25 or 0.3 or something? That can be done by using ROC curve. ROC curve takes 1 minus specificity on the x-axis, takes sensitivity on the y-axis. So basically what we do is we change the threshold values. We consider all the threshold values between 0 to 1. 0 threshold, 0.1 threshold, 0.15, 0.18, 0.2, exactly, and so on. 0.991. We change all the threshold. By changing the threshold, sensitivity changes. Have you observed it, all of you? When you change the threshold, sensitivity changes.
Yes.
Specificity changes.
Yes.
So at all these thresholds, you will get different sensitivity, different specificity values. So for all these thresholds, you will get this list of sensitivity, specificity values. Take 1 minus specificity on the x-axis, take sensitivity on the y-axis. An easy way to look at it is, this is the false positives found. You can simply look at that as mistakes, number of mistakes that you make. This is the true positives found. These are the kind of accuracy or the right predictions. Right predictions are on y-axis, mistakes are on the x-axis. That is what ROC curve draws. Right predictions are on the y-axis, mistakes are on the x-axis. Then what do? We decide the threshold. Let's say you take scenario A. Look at this, all of you. At scenario A, the percentage of mistakes are, let's say, roughly 15%. Take scenario A, the percentage of mistakes are roughly 15%. Percentage of right predictions are 65%. The remaining errors are 35%. For example, you're predicting whether a customer is good customer or a bad customer. If you go with scenario A, whichever threshold gives you that scenario, you're predicting whether a customer is bad or not. when they apply for a loan. How many mistakes are you going to do? That means how many good customers loan application are you going to reject when you go with scenario A?
15%.
50%, 15% good customers, you're going to reject their application. Now, bad customers have also applied for the loan. Out of them, how many of them are you capturing? Accurately, how many of them are you capturing? These are the right predictions, right? Bad customers rightly predicted 65%. How many risky loans you will give?
35%.
35%. That is scenario A. Now let us see scenario C. Scenario C, what is the percentage of mistakes that you make if you go with the threshold that will give you scenario C?
55.
Roughly around how much? Percentage of mistakes will be around 50%. Percentage of right predictions? Roughly it is coming around 90%. Percentage of errors will be 10%. If you go for scenario C, how many good customers loans you will reject? How many good customers applications you will reject?
50%.
50%. How many of the bad customers you will capture?
90%.
90%. How many risky loans you will give? How many bad loans you will give?
10%.
10%.
Now what we do is the threshold whether you should go for A or C depends on your type of business. Imagine you are a new bank, entered the market very freshly. You're a new financial institute. You are competing with very, very big brands. You want as many customers as possible. As many customers as possible. You're ready to take the risk. You're ready to give a loan to a risky customer. In that case, would you go for scenario A or scenario C?
A.
At scenario A, are you rejecting a lot of loan applications? Or are you approving a lot of them?
Approving.
Approving. Are you giving a lot of risky loans? Let's say if you are Bajaj Finserv or Tata Capital, which scenario would you go with?
A.
A. So whichever threshold gives me this much of unmanaged specificity, this much of sensitivity, whatever is that threshold, I will choose that threshold. Are you with me, everyone? Threshold is not decided in a standard manner. It depends on the problem statement and the business that we are handling.
Yes.
Imagine you are already an existing bank. You have lakhs and lakhs of customers. You don't want to take any risk. You don't like, let's say you're an SBI bank. Do you think they will take any risk while giving the loan? They don't want any risk, isn't it?
No.
They keep very, very stringent process. Only if the customer is absolutely perfect, then only I will give the loans. I'm not afraid of losing the customers. Do you think SBI is afraid of losing a customer? Will they be worried if a customer leave them?
No.
Not really. In that scenario, which threshold would you go for? Which scenario would you go for if you are SBI? See, how much of the loans are you rejecting? Loan applications, good customers, how many of them are you losing?
50%.
But are you worried about these guys?
No.
No. How many risky loans are you giving?
Only 10%.
Only 10%. Do you agree? Though it is both of them are loans business, one company want to reject less number of people, they take risk, they will go for a threshold that will lead to this sensitivity. In some other company, they will go for a threshold that will lead to some other sensitivity. Are you with me? Threshold is decided after a lot of discussion with the business and looking at this ROC curve and all that. Yes or no? I'm not sure as a data scientist, we will be involved in deciding this threshold, etc. Generally, that comes from the business, but those business guys are going to look at this ROC curve and come up with that result. Are you with me? This is kind of medium scenario. Okay. Depending on the situation, depending on the business, you will be picking up that threshold. But generally, we are not into that mode of picking the threshold. But there is another connected measure to this that we generally use. What is it? If you look at two models, this is model M1, the black curve is ROC curve for model M1. The red one is ROC curve for model M2. Look at this scenario. At this scenario, model M1 is making how many mistakes? What percent? Roughly 15%. Model M2 is making how many mistakes? Roughly lesser, isn't it?
Yeah.
For the same type of sensitivity, model M1, which model is making more mistakes at this level? Model M1. Look at this sensitivity. Which model is making more mistakes?
M2.
Look at this one. Model M1 is making this much. Model M2, check this. Model M1 is making roughly 35% mistakes. Model M2 is making how much mistakes? 15 only? Yes or no? Red one is model M2. Yes or no? Look at this scenario. Model M1 is making how many mistakes? Model M1. Roughly 50%. Model M2. So at every scenario, which model is making more mistakes? Tell me.
M1.
At any given level, A or B or C, is it fair to say M1 is making more mistakes than M2? Are you with me, everyone?
Yes, sir.
So if you look at the area under this curve, the area under this curve, that has to be a higher value or a lower value for a good model?
Lower value.
Which one has lower value, M1 or M2 in this case? Look at this area under this curve. M1 has, this is the area that is covered by M1. What is the area covered by M2? This is the one, isn't it? So the area has to be higher or lower? Think again and let me know.
Higher, higher.
It has to be higher, isn't it? Higher means what? You are away from this. That means you are making lesser and lesser mistakes. Makes sense? Yes or no? Let's say if I have another model that goes somewhat like this, that is M3, I would rather prefer M3. Yes or no? Because M3 is making even lesser mistakes compared to M2. So area under the curve, can I use it as a validation measure? Yes, you can use area under the curve as a validation measure. When you're comparing model M1 with model M2, sometimes area under the curve is also used as a validation measure. The area under the curve has to be what? Higher value or a lower value?
Higher value.
The advantage of area under the curve compared to accuracy. What is the advantage? Accuracy is at one given threshold. Yes or no? Accuracy is at one given threshold. Either at 0.5, you fix the threshold, then you will predict how many times 0 predicted as 0 and so on. But area under the curve, is it fixed to one threshold? It is considering all the thresholds. Think of it. To create ROC curve, we have to pick all thresholds. Yes or no? That's why ROC curve, like sometimes you'll get this interview question. Area under the curve is also there. Accuracy is also there. Which one to use or which one is better or what is the difference? The difference is accuracy can be tweaked if we change the threshold. Yes or no? If I change by changing the threshold, can I make the model look better in terms of accuracy wise?
Yes, sir.
Accuracy can be changed. If you change the threshold, does accuracy change? All of you acknowledge this point. If I change the threshold, does the accuracy of the model change? Accuracy value?
Yes.
Yeah. But area under the curve considers all the thresholds together. Area under the curve is a single value for any model. Accuracy can be multiple values depending on the threshold. That's the main difference. So area under the curve here is ROC curve. I'm not really sure you will be deciding this particular threshold and all that in reality, but sometimes you may be using this area under the curve as an alternative validation measure. So area under the curve has to be a higher value when you are comparing two models. So area under the curve can also be calculated using this Python formula. So go ahead, calculate the area under the curve for this model. For a good model, once again, tell me AUC should be a higher value or a lower value for a good model?
Higher value.
Higher value. How much is the area under the curve that you got?
0.84%.
84%. Is that a good value? 84% area under the curve is good generally. Anything above 80? I have introduced only accuracy in the previous lectures. We are introducing different methodologies because accuracy is not the right solution for every scenario. Okay, that's the main point that I want you to observe here. And to be honest with you, let's say you're building a model that will predict the number of customers who responded to a marketing call, the number of customers who did not respond, non-responders. When you make a call to 10,000 customers, tell me exactly 5,000 will respond, 5,000 will not respond. Will there be a balance, or what will be the real life scenario? Tell me. When you make a call to 10,000 customers, what will happen in reality?
Maximum will be non-responding.
Maximum will be maybe 9,000 will not respond. Hardly 1,000 will respond, or even less than that. Do you agree with that?
Yes.
And
Yes,
do you think, do you consider this as class imbalance?
Yes, with the class imbalance.
Yeah. Will
Yes,
you go for overall accuracy of this model, or would you be focusing on one class?
One plus.
Which class?
One class.
Which class is that? Which is responder sensitivity, isn't it? So let's say if you consider 10,000 customers, give you a loan. Do you think the bad customers and good customers, exactly 5,000 guys will be bad, exactly 5,000 guys will be good? Is that going to happen in reality? Tell me, all of you.
No.
No, sir.
No. What will happen? Tell me.
Bad will be around.
Bad will be
low.
around 1,000, very much lower. This will be very much higher. Do you consider this as class imbalance, or it's a balanced data? Would you consider
a class
accuracy here,
imbalance.
or would you
Class
consider
imbalance.
class-wise? Class imbalance, isn't it?
Class imbalance.
Imagine you take 10,000 patients and you're studying heart attack or stroke kind of prediction. If that is the case, how many customers or how many patients will have actually stroke? How many patients will not have no stroke? Tell me. Do you think exactly 5,000 will be the case? Is that going to happen?
No.
What
No,
will
sir.
happen? Very few.
Imbalance.
This will be few. This will be large. Do you agree in most of the real life scenarios, we will be encountering imbalanced data rather than the balanced data?
Yes. Yes.
Isn't that
Yes,
natural? It is natural,
Yes.
isn't it? We have to learn the art of handling these imbalances. Yes or no? We have to learn different validation metrics that are suitable for imbalanced classes. Are you getting the importance of this particular lecture, all of you?
Yes.
Yes.
Let me tell you a little other ways of handling the class imbalance. Just a second. Here are some other ways of handling the class imbalance. What is it? What you can do is, let's say you have a data set. Let us take the loan scenario only. Seriously delinquent. Seriously delinquent. 1 means the customer is bad customer, seriously delinquent. 0 means the customer is good customers, which means non-delinquent. These are all good customers. These are all bad customers. Usually, good customers will be more, bad customers will be less. Directly, if you build a model on this, obviously, model will not be giving you good prediction. It will not learn a lot of patterns from here. Why? Model will think that most of the data is dominated by this. Model will try to learn all the patterns related to this. So in that case, what you can do is, let us suppose you have 1 lakh records. Okay. Around 90,000 records are zeros. 90,000 records are zeros. 10,000 records are ones. 0 means good customers and 1 means bad customers. Do you really agree it will be like this in reality? When you give loan to 1 lakh customers, 90,000 will pay back. Is that really the scenario?
Yes. Yes.
Most of the cases, that is a real scenario. Even it will be less than 10,000. In most of the cases, the bad rate will be less than 10%. But when you build a model on this, the model is not going to give you good results, especially identifying the bad customers. So in this case, what you can do is you can do undersampling of the dominating class. What do you mean by undersampling? Out of 90,000 records that you have, don't take all those 90,000 guys. Take only half of them. That means you do undersampling of dominating class. Randomly pick how many guys out of 90,000?
45,000.
45,000. Then you do oversampling of the inferior class. What do you mean by oversampling? You have only 10,000 records. Repeat them multiple times. 4 times you repeat them. Though there is only one customer, what are you doing? You're saying that there are 3 other customers exactly like him. So what would you do? 10,000 records, you will repeat them 4 times. How many records are you going to make out of 10,000?
40,000.
There is only one customer with age 35, but he defaulted. How many of them are you? You will say not only this guy, there's one more customer with 35, there is one more customer with 35 like that. You're going to add 4 customers. You're going to make 40,000 of them. Then overall, how many records? Now, original
95.
data is like this. Overall, how many records are there?
95.
85,000, no? 85,000 records. When you build a model on this, now imagine model M1 here, imagine model M2 here. Which model has higher chance to pick up the bad guys? Which model has higher chance to capture the bad customers? If there is a bad customer, which model will very much surely capture him?
M2.
M2 model. Because you are exposing more and more bad guys, there is a high chance you are giving to model to learn this. Okay. But M2 has one risk. Tell me what is the risk of M2? What is the risk? Even good customers, it may predict them as bad customers. Yes or no? Are you
Yes,
with
sir.
me, everyone? But are you worried about that generally? A little bit, but not as much as, you know, the guy's bad customers, isn't it? This is known as oversampling, undersampling. Very simple concept. Basically, the blue color here indicates these are all the bad customers. This is inferior class, the class that is less frequent. You do the oversampling of them. The remaining rows are superior class. You do the undersampling of them. Then you combine these two. This will be the balanced data. Then you build a model on this balanced data. In our credit risk data set, if you see in the overall actual data, 1,50,000 rows are there. Out of them, 1,39,000 are of class 0. Only 10,000 are of class 1. That means 93% is class 0, roughly 6.6%, 7% is class 1. Obviously, this data is suffering from what problem? Your model or this data is suffering. No, is this overfitting? We haven't built any model, but by looking at 0 and 1, what is this problem called? This is the problem of
Imbalance.
class imbalance, isn't it? This is class imbalance. Now, what are we going to do? Out of these 1,39,000, roughly 1,40,000, we will take only half of them. That means class 0. Finally, how many of them I will get? Class 0, roughly 70,000. And class 1, 10,000 customers are there. I'm going to make them as 4 times. Okay. What will happen? That will be 40,000. Okay. Like exactly 4 times or 3 times. That is like, we don't need to exactly make 70, 70 and so on. Okay. A little bit of imbalance is agreed, isn't it? Precisely exactly 50%, 50% not required. Roughly you can take like 70, 40, that should be fine. So what am I doing? I'm taking 50% of the first class and 4 times of the second class. Overall, the balance data will have 69,000, 70K of one class, 40K of other class. by building a model on this, I will have better results. Do you agree with that, all of you? Is the concept understood? The concept of oversampling and undersampling? Yes, all of you? Are you clear on this?
Yes.
Go ahead. Execute this code. Code wise, if you go through it, it's not that difficult. I'll explain you once the code part. This is just trying to find out the frequency, how much percentage is 0, how much percentage is 1. After that, I'm taking a subset, class 0. I'm taking another subset, class 1. Do you understand this filter condition? Go to the loans data where serious delinquency is 0. Go to the loans data where serious delinquency is 1. These 2 lines of code, clear on this?
Sir, I have a question.
Yeah.
Sir, while going for oversampling,
Hmm.
we are taking 4 times. Is it
Depending
the
on
standard?
the scenario. Huh.
Okay.
Depending on the scenario. For example, you have a scenario where you have 1 lakh records. Okay. 70,000 are of one type, 30,000 are of another type, or let's say 75,000 are here, 25,000 are here. Tell me what will you do when you're undersampling 75,000? You can take roughly how much?
37.
Maybe 37, or maybe a little higher than that. Maybe you can take 50,000 out of these guys. Okay. You're not taking exactly half. You're taking maybe 1.5 times. Okay. Like let's say this 25,000, what will you do? Maybe you can oversample them. Maybe either you can double them, or maybe you can do like make it increase to 40,000. That is also fine. It need not be exactly always half, always 4 times, depending on the scenario. Okay. So let us
in that scenario, we need to take some authorization from the business as well, because
yes.
ultimately
But
impact the
usually
business.
these things does not matter in the final model. There will be only little differences. For example, you have done this, okay, built a model, whereas I have gone with 35K and 50K. Now that will be a problem because we are completely dominating this one. That should not happen, isn't it? Like the original class is lesser and the other class is higher. That will be too much. Maybe if somebody goes with this one, someone else goes with 40K and 30K, roughly the results that are coming out of 50K, 40K, this scenario, mostly it will be same. Unless until somebody is going ahead with very less, like from 75, you're taking only 20K. From 25K, you are increasing up to 60K and so on. Definitely this result will be different. But overall, these results, like roughly, if there are almost same proportions, then you will not see huge differences. Okay. So in our example, we have taken something like 70,000, 40,000. The results will be similar even if you take 65,000, 35,000. Okay. Or the result will be similar even if you take 80,000 and 50,000. The results will be somewhat similar. Okay. Mostly everything that is subjective decision, it's not just the data scientist who takes. We definitely get in touch with business and then talk to them. Even when you're doing the project, try to assume the best possible scenario and then go ahead with that assumption. Okay. Whichever is kind of suitable. Okay. Based on,
area under
you know,
curve is better.
yeah, please go ahead.
I think like area under curve thing is better than this oversampling and undersampling.
So basically what happens is, for a particular type of problem, particular type of methodology works. We cannot really promise that area under the curve, changing the threshold is the only thing that will work for every problem in this world. Okay. For some set of problems, for some data, maybe changing of threshold works. Okay. For some other data set, changing of the threshold also doesn't have any impact. Maybe oversampling, undersampling works. Okay. There's one more method that I'm going to tell. Maybe that works in some other scenario. It all depends on that particular problem that is in our hand. Okay.
Like, isn't it like we are artificially changing the data?
Exactly. We are artificially telling the model. We are kind of telling a lie to the model, isn't it? Really, are they really 40,000 records? Is it really 65%, 35%? Is this the real distribution? What is the real distribution? What is the real distribution? 93% and 7%. That is the real distribution. This is reality, but we are artificially telling this. That means the model is getting cheated. The model is thinking that class 1 is important and it will give you higher accuracy for class 1. Overall accuracy will reduce. Overall accuracy reduces, but accuracy of class 1 will increase. Do you really like that scenario? Think about it. Overall accuracy reduced, class 1 accuracy increased. Do you want that scenario? That's what we want, isn't it? We are cheating the model for a purpose. What is the purpose? We are very much interested in which class?
Class 1.
Class 1. And that purpose is getting solved. Are you with me?
Yes.
One is ideal scenario, not a useful model. The other one is cheating scenario, useful model. Which one is preferred in the business? Obviously, we are doing
Useful
this
model.
for a purpose. Does that make sense to you now? Think about it.
Yes, sir. Yes,
Yeah?
yes, sir.
We are willingly, purposefully telling a lie to the model. We are telling the model, learn the patterns around class 1. Earlier, you are ignoring it, thinking that it is just 7%. Now you have to focus on this. We are telling that for a purpose. Okay. Which is done. Okay. If you remember, what was our initial specificity? Tell me, what was our initial specificity without any action? Initially, specificity, what was it earlier? You remember that specificity? Where did we start initially without any action?
False negative.
How much was that specificity? How much percentage was that?
14%.
14% is where we started, isn't it? 14%. All of you, do you remember that? For this problem, 14% was the initial specificity. Then we changed the threshold. Somehow we moved it from 14 to
35.
35. But we are not really satisfied with 35, isn't it? But somewhat it is better. Now by using oversampling, undersampling, you are pushing it further to how much is the specificity right now?
35.
Specificity, how much for this model after oversampling, undersampling?
55.
55%. Check that out. Yes or no? From 14 to 35 to 55. We're trying different methodologies so that we can improve this. Is there a guarantee that whenever you do oversampling, undersampling, it has to increase? It will always increase. Is that going to work for every problem? When you're trying on your project, can you expect it to definitely grow exactly the same way, almost double? Will it happen in reality? It may not. Okay. Not everywhere threshold may work. Not everywhere oversampling, undersampling may work. We have to keep on trying until the method that we find which is improving. There is one more method that is very widely followed. That is known as synthetic minority oversampling technique. Synthetic. What do you mean by synthetic? General English terms. Synthetic means something artificially created. What we are going to do is we are going to create synthetic data. Earlier, have we created any data artificially, or we simply repeated those rows? Earlier, we simply repeated or duplicated. But now what are we going to do? We are going to add new customers. Synthetically, we'll create data. We will create data jabardasti without having the data in the actual data set. We will create it. Isn't it another level of cheating? Again, it is like we are creating some data, but why are we doing all these steps? Tell me. Are we doing it? What is the purpose? Because to get higher accuracy for a class that is interested. For us right now, specificity is important. That's why we want to synthetically create new data points. For example, he is customer 1. He happened to be a, let's say, defaulter. Customer 2, he happened to be a defaulter. Now, customer 1 income is this much. Customer 2 income. Monthly utilization. Do you understand what is monthly utilization? Monthly utilization 60% means what? Monthly utilization 60% means if 1 lakh is the credit limit, on an average, he is using 60%. On an average, he is using 65%. Actually, defaulters, here we are denoting them as ones. Okay. Now, what are we going to do? We are going to create a synthetic customer 3. This customer was never existing, but we are creating him. You know, how are we creating? I'll take these two customers' average income. How much is that? I'll take these two customers' average utilization, this much. And I'll also note him down as a defaulter. This is the new synthetic sample that we are creating. We are assuming there will be one customer who might be earning this much, who must be having this much monthly income. I'm giving you a simple example here. We have to do this from the every variable point of view. Are you getting it, all of you? We have to do it from every variable point of view. Based on that, he will be called as defaulter. This is a synthetic sample that is added. Once again, give me the justification. Why are you adding synthetic samples like this? Why can't you work with the original data set that you have?
Because we are interested in a particular class.
We are interested in particular class. That class is having lesser records. We are interested in class blue. Red class is dominating. Class blue is what we are interested in. So what we do is between these two customers, we'll add 1 point. Between these two customers, we'll add. Between these customers, we will add synthetic minority oversampling technique. Is the term clear to you right now? Synthetic minority oversampling, SMOTE technique. It is generally known as SMOTE. But the concept behind it is pretty simple. Yes or no? What we generally do is we take the customers and we synthetically generate new data points. Again, there's no rule that it has to work everywhere. Sometimes it works, sometimes it may fail also. So what we do is we take any point, we take 5 points near to it, and then based on that, we create nearby points in between points. So for example, if your original data is of the size like this, 1,39,000 records, 10,000 records, you have to use the function called SMOTE.fit resample. Give the train data, test data, automatically it will generate, like earlier from 10,000, it has generated this much. But I would say this is too much. Like there is imbalance, but we don't want to balance 100% also. That is also not a good scenario practically. What that will do, that will give too much less preference to class 0. That also we don't want to happen. So what you can do is, right now in SMOTE, we did not mention anything. We just mentioned random state to generate the same sample again. We can give one more parameter called sampling strategy. If you give 60%, what it will do is it will simply take the original class and make this 60% of this. Okay. Original class has 1,39,000 records. 60% of it is what we are keeping. Originally, earlier it was 93 versus 7, isn't it? 10 times lesser. Now it will be kind of 60% of it. Okay. Earlier it was like 7 or 8% or like 10% of it. So instead of creating 1,39,000, if you give 60% or 0.5, again, is this 60% fixed? Do we need to give that everywhere? Not the case. Okay, you can change it like 50% or 60% or 65%. So this is the original data. These are the samples that are regenerated. We don't really need to write the code for generating these samples. It is a SMOTE function that is available. Use that SMOTE function, supply your X and Y data, you will get it. Okay. Sometimes again it may work, sometimes it may not work. Previously from 14 to 35 to how much was the latest specificity in the previous example? 56%. So if we are somewhat lucky, then we may get a better one. Or SMOTE also, I have seen it works as equally effective as oversampling, undersampling. So go ahead, apply SMOTE also and see. SMOTE is like a kind of parallel technique. Like it's also oversampling only. 56% from over and undersampling. From SMOTE technique, what is the specificity that you got? Specificity from SMOTE technique. Again, here it is 56%, is it? Even from SMOTE specificity, 58, a little better. So these are some of the validation techniques. And there is a question that very frequently comes in interview. How do you handle the problem of class imbalance? Tell me some methodologies. How do you handle the problem of class imbalance? Tell me some methodology. One of the methodology is you can change the threshold value to a lower or higher value depending on the class that is important for you. The other methodology is what? Changing the threshold is one. What is the second methodology? You can try the one that gave us this one. You can try the oversampling and undersampling technique. Oversampling of inferior class, repeat it multiple times. Undersampling of superior class. The other technique is SMOTE technique, synthetic minority oversampling. You're creating synthetic samples. Okay, these are some of the ways of handling class imbalance, and that is one of the critical skill because most of the data sets are having class imbalance in real life. That is true. And when we are dealing with model validation, is it always the train data only that we look at? What is the most important thing? There are two different type of data sets. We already discussed this, isn't it? There are two errors. What is it? One is
Type 1,
train error, data set, train data set, error on the train data. Do we really build the model on the overall data every time? Is that what we're going to do? Is that a good idea? No, we divide the data into train data, test data sometimes known as validation data, train data, test data, build the model on the train data, build the model on the test data. When you are building like this, then you will realize there are certain type of problems that model suffers from, isn't it? When you look at the train accuracy, test accuracy, what will you realize? Sometimes the model is suffering from the problem of overfitting, isn't it? Tell me, what is overfitting? What is overfitting?
accuracy is higher on the train data.
On the train data, the accuracy is very high. Something like 90% or 95% or 100%. On the test data, the accuracy is
very low.
Significantly low, isn't it? Significantly lower, 60%. It doesn't match. It is 75% or 65%. Then this model is suffering from the problem of overfitting. If you make small changes to the data, the model itself changes. Sometimes these models are known as the models with a lot of variance. Model with a lot of variance means the model that is overfitted. In some of the academics, you will see model has huge variance. If somebody says model has huge variance, how do you understand that? The model is suffering from the problem of overfitting. Okay. Later on, we have also discussed another problem. If you make the model too simple, To avoid overfitting, if you make the model too simple, what will happen? So this is a code for splitting into train and test data. Okay. If you make the model too simple, what will happen? To avoid overfitting, overfitting happens if the model is too complex, if the decision tree is too big. If you make the decision tree too small, what will happen?
Underfitting.
The model will be underfitted. What is the problem of underfitting?
Very low accuracy on the train data.
On the train data, there is very low accuracy. On the test data, you don't even need to see that, because when there is very low accuracy on the train data, there is no way you will have higher accuracy on the test data. That is known as underfitting. Sometimes in academics, that is known as the model that has huge bias. Model with huge variance is overfitting. Model with huge bias is underfitting. Usually overfitting, underfitting, underfitting are the ones that are usually used. Sometimes you will also see model with variance, model with bias. So model, tell me, it has to be overfitted or underfitted? Should it have variance or bias?
It should be optimal.
It has to be optimal. Neither variance. It should be neither overfitted. It should be nor underfitted, isn't it? It has to be optimal. That is known as bias variance trade-off. That means the model should not be too simple, not too complex. That means the decision tree should not be too big or too small. And we know how to get that, isn't it? Bias variance trade-off. Bias variance trade-off means what? It should not be having high bias. That means model should not be underfitted, not having variance. It should not be having very high variance. That means the model should not be overfitted. It has to be optimal. That is known as bias variance trade-off. How do you do that? You look at the train accuracy, you look at the test accuracy, and try to find the optimal model, build the model, validate the model, keep on changing until you find very high accuracy on train data and similar accuracy on the test data. I'm not going through this because we already discussed that in depth. All of you are comfortable with this, isn't it? Overfitting, underfitting concept. Yeah.
Yes.
There is one more methodology. It's a kind of, we have seen the validation. That is the validation that most of the people follow, hold out data, cross validation. You have train data, test data, or hold out data, build the model and validate it here. This is the one that most of the people actually follow. There is one more very hardcore version of it. You may not use it, but it's good to know. Okay. There's one more version called tenfold cross validation. What is tenfold cross validation? How does that work? Instead of validating it once, one cross validation is like you have trained data, test data. That is one cross validation. We repeat it 10 times. How do you do that? Take the data, break it into 10 pieces. Let's say if you have 1 lakh records, if you break it into 10 pieces, how many records are here? Out of 1 lakh records, you have 10K records here, 10K, 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 and so on, 10K, 10K. Take the first 90,000 records, call it as train data. Last 10,000 records, call it as test data. Build a model, validate the model, fine tune the model, try multiple iterations. Stop when you have highest accuracy on train data, matching accuracy on test data. Stop it there. Next time, take 90% of the data. But this time, what will be your 90%? Are you going to take the same 90% of the data? Are you going to take same 90,000 records? No. What will you do? First 80,000 plus last 10,000 will be your 90,000 records on the train data. Then what is test data? This 10,000 is test data. Is the model that we are going to build here, is it going to be exactly same here? Or is there a slight difference in the data? Tell me. There's a little difference in the data, right? Rebuild the model from scratch. Try multiple iterations. Go for highest accuracy on train data, matching accuracy on test data. Can you tell me model M3, how many records will be there on train data? In model M3, how many records are there in train data? Number of records in train data for model M3?
Same 90,000.
Same 90,000, but which 90,000?
Maybe
That
the
will be
first
70,
last 20.
last 20. That will be train data, and then test data will be this piece, isn't it? Then rebuild the model M3. Then look at the scenario where you have highest accuracy on train, matching accuracy on test. Repeat it 10 times. For model M10, what will be the train data for model M10?
The last 90%.
Last 90%. First 10% will be test data. Again, repeat it and find out the, try to rebuild the model again. How many models are we building? Are we building one model or 10 models here?
10
models. Build the 10th model. And then highest accuracy on train data, matching accuracy on test data. Take the average of all this, which is like 85% is the average. So what we need to do is we have to build the 11th model. Let's say if this decision tree, you keep on growing the decision tree until you reach an accuracy of, until you reach which accuracy you will keep on building this model. Once you reach an accuracy of 85%, then you stop it. Then is it fair to say this model is a perfect model, which is neither overfitted nor underfitted. Can I make that statement? The 11th model that I'm building, it has an accuracy of 85%. Can I confirm that as one of the perfect optimal model?
Yes.
Think of it. How many times have we actually validated it?
10 times.
10 times. So that is how you can find the optimal model. But is it really required? Do people really follow that? Not really. As a concept, it exists. But what is the most widely followed concept in real life scenarios? What is the most widely followed concept? How do you find the optimal model? By using train data and
Yes.
test data. This is just as a concept, you can understand this. This is known as 10-fold cross validation, or in general, it is also known as k-fold if you are making it into k number of pieces. But that generally is not really is used in every case. For you in your project, you can ignore this. You can focus on the actual train data, test data, or train data, holdout data, cross validation. These are some of the validation techniques. These are some of the extra validation measures apart from the confusion matrix and the accuracy. Have you found these extra validation measures useful? Have you understood the importance of doing this extra validation measure? Do you think this must be done in your problem statement project as well? Yes. Or these are not required? Think of it. If there is class imbalance, you must focus on the class that is very important for you. Okay. So in case of class imbalance, you must focus on one particular class and you put every effort to increase the accuracy of that particular class. And the other validation measures that we have discussed here, most of them are actually discussed in the interviews. There are two topics that almost pop up in most of the machine learning or data science related interviews. One is data cleaning. The other one is model validation. And most of our students, if there are any questions that are asked on these topics, our students tend to get into a very big kind of explanation that what gives you a lot of brownie points in the interview, because these measures are very important when you're working on real life data sets and the problem statements.